Okay, now let's talk about the z-score. Z-score is something that I've already explained. Z is equal to, if you have a random variable x, you subtract its mean and divide it by standard deviation. Why do we use Greek letter mu and sigma, Greek letter sigma? Well, it's just stuck. It's a convention. When you have a random variable, its expectation value is often written as mu, and its standard deviation is often written as sigma. Okay? Now, I already explained what this does. Subtracting mu makes the center go to 0, right? And then dividing by sigma, it shrinks it down so that the width is now 1. Okay? So what this does is, if x follows the normal distribution with mean value mu and standard deviation sigma, then z would now follow the standard normal distribution. So for example, if I want to, so if we want, for example, probability of x less than some value c, then we have two options. Option one is to take simply the probability density function from negative infinity until c. That's how you calculate the probability, right? If you have an interval from a to b, just integrate this probability density function from a to b. That's how you do it. Okay? But we don't want to do this. It's awful, right? So option 2 is to do the following. Option 2 is to do, say, if I subtract mu both sides, this inequality will still be preserved, right? And if I divide both sides by sigma, this inequality will still be preserved, right? But what do we call this? This would be z less or equal to c minus mu over sigma, right? Do you agree? But this is better because z follows what? n0, 1. Okay? So this would be integral from negative infinity to this some normalized value c minus mu over sigma. That does look a little awful, but look, this part is cleaned up. This part is cleaned up, right? So this one is better because we have a table for the values of this. Okay? That's the table that I handed out just now. Okay? Is that okay? And if this calculation, this equal to this equal to this, doesn't sound so nice for you, here's another way to think about it. You can just go from here to there straight away by setting u as x minus mu over sigma. If you do this change of variables, then this c will change to this. Negative infinity will still be negative infinity, and everything will work out, and you get exactly this integral, except that instead of x you're going to have u, but that doesn't change the value of the integral. Whether you have an x here, t here, u there, it doesn't matter, right? So that's another way to see it. These two integrals are exactly the same. Nowadays, your TI-84 calculator can actually just do this right away. This is called normal CDF. Okay? So you can use the normal CDF function to calculate this integral for any sigma, any mu, any interval. That you can do that. Okay? But I want to show you the classical way before when like in the 70s when we didn't have such calculators and let's say you had to work with charts. Okay? In the old-fashioned way, what we would do is we have various values of this thing, and then we just use a table to figure out the values. Okay. Any question on this? Because now I'm going to do a word problem using this one. All right. Let me show you a word problem. Okay. A certain species of turtles have weight average of how heavy is a turtle?
What kind of turtle?
Huh?
What kind of turtle?
We're talking snapping turtles, sea turtles.
Sea
I don't care. Let's just say 3
It
pounds.
needs to be 100.
So some small breeds, 3 pounds. Okay. With standard deviation, Asian 0.2 pounds. Okay. So first question is A. What percent of weight distribution follows N3 0.2. Okay, so it's normally distributed. Okay? And it's a valid assumption, like things like weight and height and stuff like that, length. These are normally distributed. If it's not exactly normally distributed, it might be skewed a little bit. You might have some outliers, but still normally distributed does a good job. Okay, so what percentage of turtles weigh 3.1 pounds or more? And then B, what is the 75% quartile? It's also known as Q3. See, Q1 is the 25%. So if you went from the lightest to heaviest, the right in the middle will be what's called a Q2. Q2 is same as the average. Or no, that's not same as average. It's called median. But because bell curve is symmetric, the median and the mean value will be the same for bell curve, for normal distribution. And then Q2 would be like lower 25%. That's called Q1. That will be Q1. Lower 25% is called Q1. Upper 75% is called Q3. Okay? So if you arranged the turtles from the lightest to the heaviest, the one that comes at the 25th percent of the population. So out of say 100 turtles, this will be a 25th turtle from the lightest. Okay? That's what Q1 is. Okay? Here we're being asked Q3. What's the 75% quartile? And then part C would be what is the probability that a group of 3 turtles have total weight less than 2.9 times 3, so what's that? 8.7 pounds. Okay, let's try to answer these questions. Now imagine that you did have like thousands of turtles, and you did measure all the weight, but then after measuring their average weight and calculating the standard deviation, and observing that it's a normal distribution, this is all you reported in that paper. It seems like there's a big difference between having the entire raw data, actual data published, and just having these 3 facts: average, standard deviation, and being normal. Like there seems to be a big gap, but if it follows the normal distribution, we can answer so many things like these. Let me try to do one by one. Okay, I'll need some. Let me just now erase some parts because I want to start talking about these. Okay, so first of all, how do you calculate this? Well, this is like probability of, if x is the weight of a turtle, we're asking for the probability that this is bigger than 3.1. Isn't that right? Okay. And then if you wanted to write this in terms of the integral will be the probability density function from negative infinity to 3.1. That's how you, sorry, it's 3.1 to infinity, 3.1 to infinity, because it's above 3.1, right? So that's what you would do, but this is just really annoying. So instead of this, what do we do? Z, right? What is Z? Z would be x minus 3 divided by 0.2. And this will be less than 3.1 minus 3 over 0.2. See, if x is less than 3.1, then this entire thing will be less than this, right? And what is this? This is 0.1 divided by 0.2. Isn't that right? Which is 0.5. Okay? So what this is saying is that here's a normal distribution, and here's 0.5, and the question is keep doing the opposite. So we want this to be bigger than this, right? X is bigger than 3.1. So this is asking us to find this area in the standard normal distribution, okay? All right, so is this okay? Yeah. All right, so using the table, what should we do? In the table, can you find the value of the area under the curve for 0.5? What's the value? 0.500. What's the value?
0.69146.
Huh?
0.69146.
0.69146. Okay. So I'll say 0.6915. But that's in the table, what's given is the area from negative infinity to 0.5, right? That's what it says if you look at the description. Oh, I didn't write down the description, sorry. But that's what it is. Okay.
It says area to the left of the z-square.
Oh, it says so?
Yeah.
Okay, good. All right, so the table says it's the left of the z-score. So 0.5 is a z-score for 3.1. 3.1 has a z-score of 0.5, and it's the left of it has 0.6915 according to this table. Right? Okay, then what is this other value? What's this area?
1 minus that.
This would be 1 minus this, right? So it will be 1 minus 0.6915, which will be 0.3085. Okay? So, what's the answer? 30.85% of the turtles will have 3.1 pounds or more. Yes?
What do the columns mean on the?
Oh, so for example, if this one came out to be 0.512, what would you do? You will go to 0.51 here, and then 002 will be meeting at this. So in the table you have 0.51 here, in here, but then somewhere here there's 0.02 there. Right? So when these two meet, there's a number there. What's the number there? 0.6987. So that would be the area left of 0.512. That's how you use the compass. Does that make sense? Yes.
Ours are only like 0.5 to 0.6. Like it doesn't go up by.
Oh. Oh, sorry. So okay, sorry. So if you have 0.51, then you'll be like that. Okay. Yeah, that's how you. It's this plus this. Okay. And that's the value here. Is that okay? All right. Okay. Now, let's streamline this idea. So, see, I was trying to invoke all the calculus and stuff, but you really don't need calculus. I'm teaching the same type of thing with students that didn't take the hard calculus class, only took pre-calculus, and they can still manage to do this. How do they do it? Well, first, calculate the z-score for 3.1. 3.1 minus 3 over 0.2, that gives you 0.5, right? And then you rewrite this as probability of z greater than 0.5, just like that. Right? And then you say, oh, this is same as 1 minus p of z less than 0.5. And then you use the table to find out that this is 1 minus 0.6915, so that this gives you 0.3085. And therefore, that's the answer. That will be the more streamlined one. And a nice way to help you understand what's going on would be to draw this normal distribution, put the 0.5, here 0, put the z-score here, and then shade this area. If you shade this area, then obviously you know that if I want this area, it should be 1 minus the left side area. And because the table has the left side, that's what you do. Is it okay? All right. Now let's do the opposite. How do you find Q3? Well, that'll be like probability that x is less than something has to be 75%, right? Do you agree? Now look, search the table for the value of the z-score that will give you 75%. What is it?
0.67.
Huh?
0.67.
Thank you, 0.67. Gives you 75%. Do you agree? Give me a second. Who seconds? Do you agree with this? Let me look.
No.
No, you don't agree?
No, it's like 0.77347.
7. I agree. It's something like right between 0.67 and 0.68, right? Which one's closer?
I'd say 0.68.
I think this is closer. I mean, if you want to be more exact, you might just throw in a 5 there. just because it's right in between, just because 0.675, but this should be good, okay? All right, so that's what we want. Now what do you say? That means my z-score should be, z-score which is x minus mu over sigma, should be 0.67 for that to work. But our sigma is 0.2, our mu is 3, and now you just solve for x, which is x is 3 plus 0.2 times 0.67. Right? So that's like 1.34, 0.1. So it's 3.134 pounds. Am I right? Yeah, I think that's right. So that will be the Q3. 3.134 pounds will be this 75% quartile. 75% percentile, which is same as Q3. Okay. Now, part C. Part C, we have to work a little bit. Probability that we have three turtles, x1 plus x2 plus x3. They all follow the same normal distribution. Okay. And I want this to be, what was it?
Less
Less
than
than
8.7.
less than 8.7? Okay. So this is the question being asked. Okay. And that's same as, if I divide both sides by 3, that's same as x1 plus x2 plus x3 divided by 3 is less than 8.7 divided by 3 is 2.9. Okay? So, and the reason I'm dividing by 3 is because I prove the following facts about expectation values and standard deviation a long time ago, which is that if x1 through xn has same mu sigma and also its IID, same distribution, okay? Then expectation of their averages doesn't change. It's still the same. Okay? See, if you have a bunch of things, like x1 is about average 10, x2 is about average 10, x3 is about average 10. If you have these different things and you average them, the average will still come out as average 10. The average will still be the same because you're averaging something. But then, if you average a lot of different things, I talked about this stock portfolio, right? If you have a bunch of different independent stocks and some goes up, some goes down, then their variance goes down. So it's another thing I said there. Their variance of x1 plus xn over n would be going down by n. So this average quantity will have less variance than, Vx, Vx. And what that means is that the standard deviation of this average quantity will be 1 over square root of sigma. The standard deviation goes down by 1 over square root. Okay. So what am I trying to say here? I'm trying to say that x1 plus x2 plus x3 over 3. Another thing is that if you have a bunch of normal distributions, and if you take the average, it will still be normal distribution. That's actually a very important property of bell curves. If you have a bunch of bell curves, add them up, you still have bell curves. Okay, so this will still be a bell curve with average still the same as 3. But what's the standard deviation now? What's the new standard deviation of this quantity? question, would the standard deviation of this go up or down? Or stay the same? It will go down. Go down, okay? Taking averages reduces the standard deviation. That's how stock portfolios work. Like, it's always the volatility that crushes you. What does hedge fund do? They protect your billions of dollars that you don't have. Well, you do have. Well, who knows? Maybe somebody here is a billionaire. I don't know. But let's say you have $1 billion, right? You don't want to lose all of them at one day, right? So you want to own a portfolio of stocks so that the variance, their ups and downs are more stabilized. Okay? So that's what we know. Okay? So it goes down by somewhat. How much? How much does it go down?
1/3.
Yes, so 0.1 was its original standard deviation, right? But you have to divide it by square root of 3.
That was 0.2.
Oh, sorry, no, 0.2, yeah. This is 0.2, and this is 3, okay. So 0.2 was the original standard deviation. It goes down by square root of 3. Okay? Now, that allows us to calculate the z-score of 2.9. So what's the z-score of 2.9? Z-score of 2.9 will be 2.9 minus the average. But instead of dividing by 0.2, you have to divide by 0.2 divided by square root of 3. Somebody help me out here. What is this value? Negative 0.5. Oh, okay. So this would be negative 0.85 something.
Negative 0.866.
866. Oh, yeah, right. Of course. Okay, so you have this much.
Of course.
Yeah. This is like square root of 3 over 2, the sine of pi over 3, something like that. Anyways, so that's this value, and then now what do you do? This is about negative 0.87, right? It's close to that. So what you do is you want to know the probability that z is less than negative 0.87. Uh-oh, we have a problem. The table doesn't have the negative values. So what should we do?
Get rid of the negative.
No, we can't.
You can just ignore
We
it.
have to use, no. We have to use the symmetry, okay? So how do we use the symmetry? Here's negative 0.87, and we want to know this. This is going to be same as 0.87 on the right side, right? But then that's going to be same as 1 minus 0.87 on the left side. What's this value? Please help me out.
0.80785.
85.
85. Okay, so I'll just put 9.
Okay.
Okay, so what is this value? This is 0.1921. So that's the answer. That's the probability. All right, so that last one was a bit confusing, but here's the only takeaway you should definitely remember. You shouldn't forget, okay? This one. The standard deviation of average of n items goes down by square root of n. You divide by square root of n. Other things should be easy. You just have to remember that one. Square root of n goes in the denominator. All right? Okay, that's all for